Chemical Equilibrium Part 3, the equilibrium constant expression and the law of mass action. Okay, so let's remind ourselves of a few things about equilibrium. Macroscopic observables have stopped changing once the system reaches equilibrium. And also remember that the forward and reverse reaction rates are equal once the system reaches this equilibrium state. Now let's also remind ourselves about what the equilibrium constant really is. And remember, we derived an expression for the equilibrium constant that is the ratio of the forward rate constant divided by the reverse rate constant. Okay, and so we renamed that the equilibrium constant K, which is capital K. Experiments done by two scientists, Goldberg and Waj, demonstrated the ratio of products to reactants is always constant. So this is under a certain set of experimental conditions. Now, I've simplified this statement a little bit to get rid of some extra verbiage, but the bottom line is under a certain set of experimental conditions, the ratio of products to reactants is always constant. Consider this generalized reaction. So what I have here are reactants and products, okay? And these lowercase letters, those are coefficients for each reactant that is represented by an uppercase letter. So reactant A, reactant B, we have coefficient A for reactant A, and that's lowercase b for reactant B. So the products are set up the same way, lowercase c for product C, and lowercase d for product D. So this is a generalized reaction, because we're going to do something with this. So we can say the relationship between the value of the equilibrium constant K and the concentrations of reactants and products is this equation, which is the equilibrium constant expression. And what we have are products over reactants. So I've labeled that over here. So it's product C raised to the coefficient C power. So whatever that coefficient is, 1, 2, 3, you'd put that in as a power. Product D raised to the coefficient D power. And that's going to be divided by, in the denominator, reactant A to the A power, reactant B to the B power. So it's always products over reactants, and each product or reactant is raised to the power of its coefficient. So that is called the equilibrium constant expression, and that is the law of mass action. What happens if we reverse this reaction? So we've already said this is a reversible reaction, so why don't we just write it in the reverse order? So let's make the products the reactants and the reactants the products. And when we do that, we find out that this relationship for equilibrium constant K is still products over reactants, just depending on how we wrote it. So now A and B are products, so they are in the numerator, raised to their coefficient power, and C and D are in the denominator, raised to their coefficient power. So it's still products over reactants, regardless of how we write the equation. And so remember that this relationship is true no matter the initial distribution or relative amounts of reactants and products. So we can start with all reactants or all products, and in the end, we will end up with the same distribution of reactants and products. And so that is what the law of mass action tells us. Now, just another little reminder. Remember that we did an experiment where we started with all nitrogen dioxide or all dinitrogen tetroxide, and in the end we came up with the exact same partial pressures of each of those gases after the system came to equilibrium. So remember, in this part of the curve where the partial pressures are constant, that's the equilibrium part of the curve. So we have partial pressure versus time. The early part, that's the kinetics part. That's where the forward reaction rate is faster than the back reaction rate. Okay, so just reminding ourselves of that. So now let's talk about the equilibrium constant and the fact that it is unitless. And so this is actually very convenient. But why is the value for the equilibrium constant unitless? Now, we can explain this by saying that each concentration in the equilibrium constant expression is divided by a standard concentration of 1.0 molar. So you can see the expression down here. So here's our law of mass action expression, or our equilibrium constant expression. And all of these molarities are divided by 1 molar. And so all of those molarity units cancel. Now, instead of writing this out each time and being very explicit about it, we actually rename these to something called activities. So when we divide each reactant and product by the standard concentration, then we're left with an effective concentration, or activity, which is what these are called. And you can think of the activity as the presence of a reactant or product in the reaction. So we use activities even though we often don't write them with A's and then subscripts for the reactants. We usually just put the reactants right in brackets, just as we have been doing. But behind the scenes, we are using activities. We have divided out the units. Now, the law of mass action holds for gases in equilibrium just as it does for solutions. And so we have a new symbol to look at. And so this is the partial pressure of product C raised to the coefficient C power. Okay? So for gaseous reactions, then we would have P as the partial pressure. There's the reactant or product raised to its coefficient power. Now, again, partial pressures are going to be activities as well. So all of our partial pressures have been divided by a standard pressure, which is 1 atmosphere. And so the equilibrium constant K for gaseous systems is also unitless because we are using activities. Pause the presentation and try to write the equilibrium constant expression for this reaction. So we have the equilibrium constant K, and it's going to be products over reactants, and each of those is going to be raised to the coefficient power. So we see the coefficient of dinitrogen tetroxide is 1. So products to the first power divided by reactants, nitrogen dioxide, to the second power. So that's the equilibrium constant expression for the reaction we've been talking about. We can actually calculate a value or a number for this equilibrium constant, and we do that by inserting the equilibrium concentrations or partial pressures into the equilibrium constant expression. So once the system comes to equilibrium, then we plug in those concentrations or those pressures into the equilibrium constant expression, and then we do the math and we get a value for the equilibrium constant. What is the value of the equilibrium constant when the concentration of nitrogen dioxide at equilibrium is 0.0165 molar and the concentration of dinitrogen tetroxide is 0.0417 molar? So pause the presentation and give that a try. So let's go ahead and plug those in. So we had our equilibrium constant expression from a previous problem, and 0.0417 molar is the concentration for dinitrogen tetroxide. So we plug that in, and then we're going to go ahead and plug in 0.0165 molar to the second power, very important. Plug that in, do the math, and we end up with 153. And remember, the equilibrium constant is unitless because we are using activities, even if we don't explicitly show it. What if we reverse the reaction? We still have the same equilibrium concentrations, which we should, because under a given set of experimental conditions, the equilibrium state is always going to be the same. So go ahead and write the new equilibrium constant expression and then calculate the value for K. All right, so when we do that, now we have nitrogen dioxide as a product to the second power, dinitrogen tetroxide in the denominator to the first power. So our new equilibrium constant expression, still products over reactants, plug in our numbers, and we end up with 6.53 times 10 to the negative 3. So you might be wondering, why did we get a different number? Well, we reversed the reaction. And so if you put this number into your calculator, you're going to find out that if you take it to the minus 1, then it's the same as it was for the previous reaction. This value is just the inverse of our previous reaction, and it's because we reversed the direction of the reaction. We're going to talk about that more in the next video. So now let's use some partial pressures. Now these are not the same experimental conditions. Now we're going to put in equilibrium values of 1.26 atmospheres of nitrogen dioxide and 0.199 atmospheres dinitrogen tetroxide. So go ahead and write the equilibrium constant expression with partial pressures, and then go ahead and plug in those partial pressures. And when we do that, then we're going to end up with the partial pressure of dinitrogen tetroxide to the first power, the partial pressure of nitrogen dioxide to the second power, because it has a coefficient of 2, plug in 0.199 for dinitrogen tetroxide, 1.26 for nitrogen dioxide, and do that math, and we're going to end up with 0.125. And remember, K is unitless because we used activities, even though we have gases in our system now. We are still using activities. Okay, so the next thing we're going to talk about is the properties of the equilibrium constant.